Well, greetings, Mr. Colazar's class. Today we're going to start looking into breaking down the trends of the atomic rate or trends of the periodic table, and we're going to begin with the atomic radius. And the atomic radius definition is the measure of the atom's size. Now, it's difficult to measure one atom, so what they actually do is it's actually the distance between two nuclei of identical atoms. So the distance between one atom's nucleus and the atom of another's nucleus, since there's kind of no definite boundary between them. So half of that distance, if you cut that in half, is what the atomic radius is. Now, what we're going to look at is a trend of how it affects the size of the atom. Now, our first trend is as we're going down our periods from period 1 to 2, 3, 4, 5, 6, 7, it's generally going to increase the size of the atom. And why is that? The outermost energy level increases down the group, making each atom larger. So as we're going down the group, we start off with 1 energy level, and then 2 energy levels, 3 energy levels, 4 energy levels, 5 energy levels. So each time we go down the group, we're going to get larger and larger atoms. So that's our first trend with atomic radius. More energy levels increasing as we go down the group. Now, as we go across the periodic table, so on that periodic table you have at the bottom of your page, what you're going to write is it generally is going to decrease as you go across the periodic table. And the reason for that, why that is our 4 P's. More protons, more, or across the period, you get more pulling power. So all of those protons, as you go increasing the number of protons, it's going to increase the pull on every electron. So those protons in the nucleus, the more you have, the more they're going to pull on each electron, making those atoms actually smaller or decrease as you go across the period. So first off, going down makes our atoms larger. Going down the periodic table, going across the periodic table is going to make those atoms smaller in size. So just as a picture, you go from lithium to sodium to potassium, rubidium, cesium. Each of those are getting larger as you go down. And as you go across the periodic table, our atoms are generally going to get smaller when it talks about the radius. Now, our second idea at the top of the next page are going to be ions. Now, up until this point, we've kind of kept neutral charges because the protons have equaled the electrons. Now we're going to start changing that. An atom or a group of bonded atoms with a positive or negative charge is going to be known as an ion. So our electrons and protons do not equal each other. This is why they have that charge. So an ion is going to be a positively or negatively charged. So you're going to see things like Na with a plus, or you're going to see things like chlorine with a minus charge, or sulfur with a -2 charge could be examples there. Now, what happens to an atom? Your chart's a little bit different, but when an atom loses electrons, electrons are negative, they become positive in charge. So an example, sodium has 11 protons, 11 electrons, so there's no charge there. If sodium loses an electron, 10 negatives to 11 positives, it becomes a +1. Now, generally, you're going to decrease the size or have a smaller atomic radius. Less valence electrons makes it easier for them to be pulled towards the nucleus. Generally, just add this in as a note. Metals tend to lose electrons. So this is a good note to add in. Add. Now from there, other atoms are going to gain electrons. And the ones that gain electrons become negative. An example, chlorine starts out with 17 protons, 17 electrons, so it's no charge. If it gains an electron, so it has 1 extra, and the protons it has an overall -1 charge. If you add an electron, it's going to increase the size or make the atomic radius larger. More valence electrons makes it more difficult to pull on the electrons, and they move further away. Add this one in. Nonmetals tend to gain electrons. So if we were to look at sodium, sodium's electron shortcut, neon 3s1, it wants to lose this electron. So it's going to get smaller in size. Chlorine, neon 3s2 3p5, wants to actually gain an electron to get to 3s2 3p6, which looks like argon. And when it gains an electron, it becomes larger in size. So if we looked at each one, sodium, 1s2, 2s2, 3s1, it wants to lose that outer electron. And as it loses that outer electron, it becomes positive in charge. Note, sodium ion has the same electron configuration as neon now. So what we're looking for is having it have a noble gas configuration. So the octet rule. Atoms tend to gain, lose, or share electrons in order to acquire a full outer set of 8 valence electrons, except elements 1 through 5 only want 2 outer electrons. So 8 is great, is that key idea. They want to get to 8 valence electrons either by gaining, losing, or sharing. So magnesium starts out with 3s2. It wants to lose those 2 electrons to become a +2, and then it's going to end up looking like neon. Chlorine starts out at 3p5, so 2 plus 5 is 7. It wants to gain an electron so that in the end it's a negative charge. So chlorine's going to want to gain electrons. So this is useful for determining what type of ions we're actually going to form. Metals tend to form positive ions. Nonmetals tend to form negative ions. So example, nitrogen. What type of ion will it form? Now nitrogen, as we're looking, 1s2, 2s2, 2p3. So it's got 5 total outer electrons. It wants to get to 8, so it needs to add 3 electrons. Make that a plus sign to get to 8 electrons in its outer energy level. So nitrogen is going to form, right over the top of it, nitrogen is going to be a -3 charge, and that's written up as a superscript. Nitrogen, when it gains 3 electrons, larger than our neutral atoms because it has more electrons. Cesium is going to want to lose an electron to become positive. And when it loses that electron, cesium is going to become smaller in size. And so that's our information to begin with on atomic trends, the radius, and ions.